Section 1.3 Classifications of Matter. Matter is anything that occupies space and has mass, and chemistry is the study of matter and the changes it undergoes. All matter, at least in principle, can exist in three states: solid, liquid, and gas. Solids are rigid objects with definite shapes. Liquids are less rigid than solids and are fluid. They're able to flow and assume the shapes of their containers. Like liquids, gases are also fluid, but unlike liquids, they can expand indefinitely to occupy the entire volume of a container, regardless of the amount. The three states of matter can be interconverted without changing the composition of the substance. So that means it's a physical process, not a chemical. If you heat, for example, a solid, it'll melt. It'll form a liquid. Further heating will turn it into a gas. The conversion takes place at the boiling point of the liquid. On the other hand, if you cool a gas, it'll condense into a liquid and heat will be released. When the liquid's cooled further, it'll freeze into the solid form. They seem to be ignoring sublimation and deposition, but I think that's okay because it's very rare. Note that the properties of water are unique among common substances and that the molecules in the liquid state are more closely packed than those in the solid state. This is something I think everybody's pretty familiar with. Substances and mixtures. This is such an important point for scientists. They generally hate mixtures and generally love substances. And when they're thinking of substances, let me cut to the chase and tell you that they're generally thinking about molecules, not elements, with rare exceptions, but simply molecules. A substance, there it is, a form of matter that has a definite or constant composition. That means a pure form of matter. Examples are water, a molecule; silver, an element; ethanol, a molecule; table saw, a molecule that's more commonly called a compound; and carbon dioxide, a molecule. I like that they mostly chose molecules. Substances differ from one another in composition and can be identified by their appearance, smell, taste, and other properties. It's true. At present, over 66 million substances are known, and the list is growing rapidly. As a research chemist, what I did mostly is made new substances and evaluated their properties. It's not that hard to do. A mixture is a combination of two or more substances in which the substances retain their distinct identities. A mixture, it's more than one substance, and it's not usually particularly useful. It's not something you're thrilled about. To understand it, you generally have to separate it out. People worry about synergistic properties, things like that, but largely a mixture can be understood by simply evaluating the components therein. Of course, if it's a reactive mixture, that's another matter. Some examples are air, soft drinks, milk, and cement. Mixtures do not have constant composition. That's why you can't really study them. If it's always 80-20, for example, you're good to go. And that's the nice thing about molecules, is they have a fixed composition. You know it once, you know it forever. Therefore, samples of air collected in different cities would have different composition. And so mixtures can be confusing. Mixtures are either homogeneous or heterogeneous. When a spoonful of sugar dissolves in water, the composition of the mixture after sufficient stirring is the same throughout the solution. So now you got the difference between two types of mixtures. One would be homogeneous, with the constant composition. The other one is heterogeneous. Now, the way I've always described it is if you can see two things, it's heterogeneous. If you cannot, it's homogeneous. Let's see how they do it. Adding oil to a water creates another heterogeneous mixture because the liquid does not have a constant composition. So they don't define it in terms of what you observe. They define it in terms of what it is. Uniformly mixed, not uniformly mixed. That might be a better way to define it. Any mixture, whether homogeneous or heterogeneous, can be created and then separated by physical means into pure components without changing the identities of the components. And that's usually where the skill of a chemist comes in. Most chemists, let's face it, spend a great deal of their time turning a mixture into individual substances. I know that's what I spent, probably 80% of my time, whether I was an explosives chemist, a polymer chemist, an organic chemist, a medicinal chemist. I always seemed to be cleaning things up. Thus, sugar can be recovered from a water solution. I think sugar can be covered from a water-sugar solution by heating the solution and evaporating it to dryness. Better do that carefully to avoid decomposition, right? Making caramelized sugar. Condensing the water vapor will give us back the water component. To separate the iron-sand mixture, we can use a magnet to remove the iron filings from the sand because sand is not attracted to the magnet. Good point, and that's such an easy separation. After separation, the components of the mixture will have the same composition and properties as they did to start with. I wonder if Chang, like me, does a lab like that, where they separate a mixture and using a magnet is such a sweet way to just pull out pure substances. Elements and compounds. I hope they point out that compounds are really where it's at. A substance can either be an element or a compound. An element is a substance that cannot be separated into simpler substance by chemical means. They're trying to tell you that chemistry is not a nuclear process. We don't make new elements, we just study the ones that we have. At present, there's 118 elements that have been positively identified and several that are on the way. Chemists use alphabetical symbols to represent the names of the elements. They used to use far more obscure notation, but now they're using these 1 or 2 letter symbols. The first letter of the symbol for an element is always capitalized. That annoys scientists when they don't do that. But the second letter is never capitalized. Ca, capital C, little a for calcium, Co for cobalt. Not CO, that would be carbon monoxide. Well said, I like that. Table 1.1 shows some of the more common elements. Fine, I'm going to skip that because we'd like to go through this quickly. You don't mind, do you? Yeah. Most elements can interact with one or more other elements to form compounds. Yes, they can. And they're saying most because they're thinking perhaps about noble gases, which don't tend to do anything at all. We define a compound as a substance composed of 2 or more elements chemically united in fixed proportions. I've always found that a silly definition. See how they said 2 or more elements? Now, therefore, H2, the molecule hydrogen, is not a compound because it does not have 2 different elements. But why? What is the point of making that distinction? Compound and molecule, in my opinion, should be synonymous. Hydrogen gas, for example, burns in oxygen to form water, a compound whose properties are distinctly different from hydrogen and oxygen. It doesn't sound like they're saying much, but it is a common misconception. People think that water, H2O, should have a lot of properties of hydrogen and a lot of properties of oxygen. It bears almost no resemblance to the individual elements. It is its own thing, and that's really why molecules are so much more important than elements for a practicing chemist. Water is made up of 2 parts of hydrogen and 1 part oxygen. That is true if you're evaluating by counting atoms. This composition does not change, regardless of whether the water comes from a faucet in the United States or the Yangtze River in China, or the ice caps on Mars. Whoa. Unlike mixtures, compounds can be separated only by the chemical means into their pure components. Nice. The relationships among elements, compounds, and other categories are summarized. But if you just ask somebody, is silver a molecule or a element, they'd say element. It's not that hard to do. This concludes the discussion on classifications of matter.